AI isn't just running in the cloud anymore, it's everywhere. From tiny edge sensors collecting real-world data to distributed training clusters and cloud inference engines, intelligence is now spread across an entire hardware ecosystem. And here's the challenge. Every one of those nodes is a potential target. From a broader perspective, the AI workflow is basically a long chain of trust that consists of data generation, aggregation, training, deployment, inference, and orchestration. Break any link, and the integrity of the entire system can be at risk. That's why software-only security approaches are starting to fall short. Credentials stored in firmware, a hardwared root of trust, and OS-level protections can be bypassed if the underlying hardware isn't protected. In this tech guide, we're going to walk through how Infineon's OPTIGA TPM SLB 9672, 9673, and OPTIGA Trust M establish security at the silicon level where it actually matters.
Step 1. Why AI security must start at the silicon level.
When we talk about securing AI, we're really talking about protecting three things: data integrity, model integrity, and device identity. The challenge is that traditional security stacks assume operating system is trustworthy. But in modern AI deployments, that assumption could be false. As systems scale from edge devices to cloud servers, the attack surface expands dramatically. A compromised sensor may inject bad training data. A spoofed edge node may poison federated learning. A tampered modeled update may silently alter inference behavior. At that point, software defenses alone don't hold up. And that's where a hardwared root of trust becomes essential. Instead of just trusting software, you anchor identity and cryptographic operations directly in silicon. That's exactly the role Infineon's security portfolio plays. And it starts with the OPTIGA TPM, the foundation of trusted AI platforms, which we'll explore next.
Step 2. OPTIGA TPM, the hardware anchor of trust.
Now let's explore the core components. The OPTIGA TPM SLB 9672 and SLB 9673. These are trusted platform modules built on the TPM 2.0 standard, and you can think of them as a protected vault that resides inside your system hardware. What makes them powerful is that they isolate critical security operations from the main processor. Things like key generation, encryption, decryption, and attestation all happen inside the TPM itself, not in general purpose memory. That means even if the operating system is compromised, the keys stay protected. They also handled secure boot and measured boot, which basically means the device can verify itself before anything else runs. Additionally, they support device identity and integrity checks, taking care that every system can prove it is running trusted firmware before participating in an AI workload. So once this hardware root of trust is in place, we can start applying it across real AI security functions. We'll take a closer look at that next.
Step 3. Core security functions for AI systems.
With the TPM in place, you can start enforcing security policies that actually matter for AI systems. Let's look at some examples. You can protect cryptographic keys used for model signing so they are processed inside the security hardware only. You can also verify device identity before allowing it to join a training cluster or access cloud resources. Another key function is device health attestation. Before an edge device contributes data or runs inference, it can prove its firmware state hasn't been tampered with. That becomes especially important in AI pipelines where bad data may lead to bad models. Secured firmware updates also play a big role. Instead of blindly trusting updates, the TPM validates them before execution. And when combined with TLS-based communication, you get a fully secured channel from device to cloud. Once these core functions are in place, the next question is how they behave across real-world AI architectures. We'll dive into that next.
Step 4. Deployment across edge-to-cloud AI systems.
AI security really requires a tailored approach. The requirements at the edge are very different from cloud or federated environments. In MPU-based systems like Linux or Android edge devices, the OPTIGA TPM enables measured boot and runtime attestation. That means the system proves its integrity before it ever starts processing AI workloads. In federated learning setups, TPM-based trust becomes even more important. Only verified nodes are allowed to contribute updates, which helps prevent poisoned or malicious training inputs from corrupting the global model. And in systems like robotics or industrial controllers, TPM-based architectures extend trust across multiple connected devices. This allows secured orchestration where every node can verify the others before interacting. Once trust is established across the system, we can focus on how AI models themselves are protected at the edge.
Step 5. Secured AI model handling at the edge.
At the edge, AI models are especially exposed. They may be copied, modified, or replaced if they're not properly protected. The OPTIGA TPM addresses this by binding model execution to cryptographic identity and integrity checks. Before a model runs, it can be validated against a trusted signature stored in hardware. Keys used to decrypt or authorize model execution are stored and processed only inside the protected boundary of the TPM. Even communication back to the cloud, whether for telemetry or updates, can be protected using hardware-backed TLS credentials. So instead of treating the model as just software, the system treats it as a trusted asset that must be verified at every step. Now, while TPM handles security-relevant platforms, many IoT systems need something lighter. This is where OPTIGA Trust M comes in.
Step 6. OPTIGA Trust M. Cloud security and identity.
OPTIGA Trust M is designed for a different but equally important role. That role includes scalable device identity and cloud connectivity. It gives each device a secured, hardware-backed identity that can be used for zero-touch provisioning into cloud environments. So instead of manually configuring credentials, devices can authenticate automatically using pre-provisioned certificates stored securely in hardware. This simplifies deployment at scale while maintaining strong security. OPTIGA Trust M also makes integration easier through cryptographic toolsets and protected communication interfaces. It supports secured certificate updates, meaning devices can remain trusted throughout their lifecycle, even years after deployment. So while OPTIGA TPM protects platforms and secures the communication, OPTIGA Trust M focuses on identity, onboarding, and cloud connectivity. Together, they form a layered security model, giving engineers end-to-end control over trust from silicon to cloud.
Conclusion.
AI systems require security embedded at the hardware level from the start. The Infineon OPTIGA TPM SLB 9672 and 9673 establishes a strong hardware root of trust for platform integrity, secured boot, attestation, and AI workload protection. At the same time, OPTIGA Trust M extends that trust into scalable IoT ecosystems by securing identity, provisioning, and cloud connectivity. Together, they create a continuous trust chain from edge to cloud, taking care that every device, model, and data stream is verified and protected. To learn more about these innovative and reliable Infineon devices, head over to Mouser.com or click the link below. And be sure to check out our other tech guides because smart minds never stop learning.